Picture the most watched sporting event on the planet. 3.5 billion people, 104 games, 48 countries. And at the center of all of it, a single object that fits in your hands. Now, here is the number that changes everything. One city in China, a city most football fans cannot find on a map, manufactures over 70% of all the soccer balls sold on Earth. You heard that right. More than 7 out of every 10 soccer balls on this planet were born in the same zip code. That is not a supply chain fact. That is a monopoly hidden in plain sight. And that is just the beginning. Because the craziest part is not the volume. The craziest part is how and why and what it actually took to get there. By the end of this video, you are going to understand exactly how the ball sitting on the pitch at the 2026 World Cup was made, what is inside it, why no one else on Earth can make it cheaper, and what that tells you about how the modern world actually works. If that sounds like the kind of thing you want more of, hit a quick like and subscribe so you do not miss what comes next. Here is where the story really begins, on a factory floor in Zhejiang province, at a company most football fans have never heard of. The factory floor nobody talks about. Walk into Yiwu Aokai Sports Goods Co. Limited on a Tuesday morning, and the first thing you notice is the noise. Not machine noise exactly. Something more rhythmic than that. A low, continuous hum that you feel in your chest before you understand what is making it. What you are hearing is a soccer ball being born. Most people, when they think about where a World Cup ball comes from, picture a gleaming product laboratory somewhere in Germany, engineers in white coats, computer simulations, a CEO in a press conference holding up the new design while a brand name flashes behind him. That image is not wrong. The design does happen in Germany, or in Oregon, or in Tokyo. But the making happens here, in a city of 2 million people in eastern China that most Westerners have never heard of, inside a building that from the outside looks like every other industrial unit on the road. Here's what most people never think about. Before a soccer ball is a ball, it is a problem of physics. You need an object that can withstand being struck at over 70 miles per hour, maintain its shape through thousands of impacts, fly predictably through the air, and behave the same way in wet conditions as it does in dry ones. You need it to weigh exactly between 14 and 16 ounces. You need its circumference to sit between 27 and 28 inches. And you need to manufacture it at a price point where a 12-year-old's parents can afford to buy one. That is not a design challenge. That is a manufacturing engineering challenge. And it starts with the part of the ball that nobody ever sees. Inside every soccer ball is a rubber bladder. Think of it like a balloon inside a balloon, a sealed internal membrane that holds the air and gives the ball its pressure. But a bladder alone cannot hold its shape under repeated impact. So what happens next is one of the most overlooked steps in the entire process. The bladder is inflated. And then it is wrapped, not quickly, not roughly, but in over 10 minutes of continuous yarn winding per unit. A single ball, over 10 minutes. The machine feeds the thread in overlapping spiral layers around the entire surface, each pass reinforcing the one before it, until the bladder is encased in a textile shell that can resist deformation under impact. Now here is the part that blows people's minds. That yarn is not there for padding. It is not there for softness. It is there because without it, the ball cannot maintain its spherical geometry when you kick it. The geometry is the product. The yarn is what protects the geometry. And every ball coming off this floor gets the same 10 minutes. There are no shortcuts in the yarn room. But a perfectly wrapped bladder is still not a ball. And the next step is where the two great tracks of soccer ball manufacturing split apart, and where the story gets genuinely strange. The thermal bonding revolution. Here is something that engineers quietly disagree about. What makes a soccer ball better, precision machines or human hands? The answer, it turns out, depends entirely on what you mean by better. Modern World Cup match balls, the ones you see professionals playing with in the stadiums, are made through a process called thermal bonding. Forget everything you think you know about how a ball is put together, because none of it involves a needle and thread. Start with the panel material. A soccer ball panel is made from polyurethane, a synthetic polymer that starts as a chemical reaction in a tank and ends up as a flexible, durable sheet material that can be printed on, cut, molded, and fused. Think of it like a synthetic leather that was engineered from scratch to do exactly one job: survive a professional footballer's boot 10,000 times without cracking. The panels go through a U-shaped press, a printing and forming machine that stamps the tournament branding, the team graphics, and the aerodynamic texture patterns onto the surface in a single pass. Then they go to the thermal cutting machines, which trim each panel to within fractions of a millimeter of the required geometry. If the edge is off, the seam is off. If the seam is off, the ball's aerodynamics change. If the aerodynamics change, a professional player will feel it at 70 miles per hour. The tolerance is not a guideline, it is a non-negotiable. Then comes the fusing step. Each panel is coated in adhesive, a heat-activated compound that does nothing at room temperature and everything at 80 degrees Celsius. The coated panels are laid into a spherical mold. The mold closes. 90 seconds. Exactly 90 seconds. During that window, the adhesive melts. The panels press together at the seam, and when the mold opens, the ball's surface is seamless, not stitched, not overlapped, fused. Here is the brutal catch that nobody in the marketing materials mentions. A thermal bonded ball cannot be deflated for shipping. The internal pressure is part of what holds the fused seams in shape during the bonding process, which means every single thermal bonded ball ships at full volume, taking up as much space in a container as it will ever take up in its life. For a factory producing hundreds of thousands of units, that is not a footnote. That is a logistics equation that directly drives container costs, shipping rates, and the economics of getting a ball from Zhejiang province to a stadium in Dallas or Miami or Vancouver. The factories here have solved it, not by deflating the balls they cannot, by optimizing every other variable in the supply chain around that fixed constraint, which is itself a form of industrial mastery that took years to develop. But here is the thing. As extraordinary as thermal bonding is, there is an older technology on the floor next door that the professionals still trust more for feel. And understanding why tells you something profound about what precision actually means. The geometry of the hand-stitched ball. Before there were thermal presses and adhesive compounds and U-shaped printing machines, there was a person at a workbench with a curved needle and a thread waxed just enough to slide through leather without fraying. Hand-stitching is not a tradition kept alive for nostalgia. It is kept alive because the geometry it produces cannot be beaten for touch. Here is the concept that unlocks all of it. A soccer ball, the classic version, the one every child learns to draw, is not a sphere. It is an approximation of a sphere, built from flat materials. Specifically, it is a truncated icosahedron. That sounds like a mathematics exam answer, but stick with it, because this is where the story really begins. Take a sheet of flat material. You cannot wrap it around a sphere without it bunching or tearing. The only way to approximate a sphere using flat panels is to cut the panels into shapes that, when assembled together, distribute curvature across every seam. Mathematically, there is only one arrangement of two shapes that does this perfectly, using the minimum number of panels. 20 hexagons for contact surface area, and 12 pentagons to enforce the curvature that closes the flat structure into a stable three-dimensional form. Think of it like this. The pentagon is a forcing function, like the keystone of an arch. Without it, the hexagons would lie flat forever. With it, they have no choice but to curve. Every pentagon is surrounded by 5 hexagons. Every hexagon alternates between connections to 3 pentagons and 3 hexagons. That pattern, repeated 12 times across the surface, is the only arrangement that distributes stress evenly when the ball is struck. It was not invented by a sports engineer. It was derived from mathematics. And it is so structurally correct that it stayed essentially unchanged from the first standardized football to the 1970 World Cup Telstar, the black and white classic and beyond. Now here is what most people get wrong about modern innovation. Adidas, at the 2014 Brazil World Cup, departed from the 32-panel design entirely. They produced a 6-panel ball, cross-shaped panels, that wrapped around the bladder in a way that eliminated most of the seam length. It looked revolutionary. The aerodynamics were theoretically superior. And the professional players hated it. Goalkeeper feedback in particular was severe. The ball's flight path under certain striking conditions was genuinely unpredictable. Not randomly unpredictable, but predictably unpredictable, in a way that the players could not calibrate to. The mathematics of the 32-panel design had been doing invisible structural work for decades, and removing it had consequences that showed up not in a wind tunnel, but in a World Cup quarter-final. The workers in Yiwu's hand-stitching workshops know this geometry by touch. Each worker handles a curved needle and a thread under tension, pushing through pre-punched holes around the ball's surface in a sequence that maintains even tension across every seam. One worker, one ball, one sitting. The seam quality you get from a hand-stitched ball under those conditions is something no current machine can replicate at that price point. And that tension between the precision of machines and the precision of hands runs through every square foot of this factory floor. If the geometry of a 32-panel ball surviving a World Cup disrupted everything you thought you knew about sports engineering, the next part is going to be even harder to believe. Hit subscribe so you are there when we cover what comes next. Yiwu, the city that built the world. Here is the detail that puts everything into perspective. Yiwu is not a manufacturing anomaly. It is a manufacturing proof of concept. Most industrial cities specialize in one or two product categories. Detroit built cars. Sheffield made steel. Lyons made silk. That is how industrial geography normally works. A city develops expertise in a sector, and that expertise becomes the city's identity for generations. Yiwu did not do that. Yiwu became the world's largest small commodity market, a city where you can source nearly every manufactured object that fits inside a shipping container, from every industry, from a single address. Over 75,000 permanent booths across a market complex, covering more than 4.5 million square meters. That is an area larger than 600 American football fields, filled with nothing but sourcing offices, sample displays, and wholesale distributors, all of them connected to factories within driving distance. The soccer ball factories are one node in that network, but understanding the network explains why the factories exist at the level they do. When a supply chain concentrates in one geography, it pulls in every supporting industry simultaneously. The yarn winding machine manufacturers, the adhesive chemical suppliers, the printing press specialists, the mold fabricators, the logistics companies who know exactly how to stack inflated thermal bonded balls in a container to minimize dead space. Over decades, all of those specialisms moved to within a short distance of each other in Zhejiang province. Not because of a single government directive, though industrial policy played a role, but because proximity to the market created pull for every supporting capability, and that pull compounded year after year. What that means in practice is this. If you wanted to build a competing soccer ball factory at Yiwu's scale and quality in, say, the American Midwest or in Eastern Europe, you would not just need the building and the machines. You would need to reconstruct every supporting industry simultaneously. The specialized adhesive chemistry, the precision mold fabrication, the yarn winding engineering, the hand-stitching workforce with 15 years of seam calibration experience, the logistics infrastructure optimized specifically for full-volume inflated ball shipping. You would need to rebuild an ecosystem, not a factory. And ecosystems do not get built in a decade. Now, here is what makes this even more consequential. Soccer balls are not a strategic commodity. Nobody in a foreign ministry is writing memos about soccer ball supply chain security. Which is precisely what makes Yiwu's position in this category so instructive, because the same logic that produced this monopoly in soccer balls produced comparable concentration in hundreds of other categories, many of which are strategic. The question is not whether this happened, it happened. The question is what you do with the knowledge that it happened everywhere, simultaneously, in ways that were almost entirely invisible until they stopped being invisible. But to understand what that means for the 2026 World Cup specifically, you need to follow one ball from this factory floor all the way to a stadium in North America. And that journey is stranger than you think. From Zhejiang province to the World Cup pitch. Most people picture the supply chain for something as high profile as a World Cup ball as being extraordinarily short. FIFA selects a ball. Adidas makes it. The balls arrive at stadiums. Simple. Here is the reality. The journey from Yiwu to a World Cup pitch passes through more hands, more inspection points, and more logistical decision nodes than the ball's final 5 minutes on the pitch would ever suggest. FIFA's specifications for a match ball are not loose suggestions. They are engineering tolerances expressed in millimeters and grams and kilopascals. The ball must weigh between 14 and 16 ounces. Circumference must be between 27 and 28 inches. It must rebound between 24 and 32 inches when dropped from a height of 6 feet 6 inches onto a hard surface. Its water absorption, how much heavier it gets when wet, must stay below 10% after being dunked in water for 30 minutes. These are not marketing specifications. They are physics requirements that directly affect the outcome of a professional match. Think of the quality control process, like the calibration check on a medical instrument before surgery. You do not run it once and assume. You run it on every unit, in batches, at multiple stages. At AOKI and facilities like it, quality control is embedded in the production line, not bolted onto the end of it. Bladder pressure is checked before yarn winding begins. Panel geometry is checked before thermal bonding. Post-bonding roundness is checked using a sphericity gauge that measures deviation from true sphere across multiple axes. Any ball outside tolerance is pulled. Not reworked. Pulled. The balls that pass are boxed, palletized, and loaded. Here is where the thermal bonding constraint lands in the real world. A standard 40-foot shipping container can hold approximately 2,500 inflated thermal bonded balls. The same container, if it were shipping deflated hand-stitched balls, could hold closer to 10,000 units. That is a 4-to-1 difference in container efficiency, meaning the per-unit shipping cost of a thermal-bonded match ball is structurally higher than a comparable hand-stitched ball, simply because of the physics of the bonding process. Factories here have compensated for this through volume. The more units you ship, the more efficiently you can fill containers and routes, which is itself a reason why small competitors cannot match the economics even if they replicate the process. From the port, the balls move to regional distribution centers typically in the host country, where Adidas or the relevant brand partner conducts its own final inspection before the balls are allocated to tournament venues. At this point, the ball has been touched, measured, and approved by people in at least 3 countries before a footballer has kicked it once. Now here is what makes this incredible. None of that complexity, none of the precision, none of the logistics engineering, none of the quality infrastructure appears anywhere in the product. You see the ball. You see the Adidas logo and the FIFA badge and the 2026 tournament branding. The factory is invisible. The city is invisible. The 10 minutes of yarn winding is invisible. Everything that made the ball possible was designed to disappear. And that invisibility is not an accident. It is a feature of the system that built it. Why nobody can replicate this? Here is what most people get wrong about manufacturing dominance. They think it is about cheap labor. That is the simplest version of the story, and it is also the least accurate version. Labor costs in Zhejiang province have risen significantly over the past 20 years. They are not at Western European or North American levels, but they are not where they were in 2005 either. If cheap labor were the only variable, the soccer ball industry would have moved to Vietnam or Bangladesh or Cambodia a decade ago. Parts of it have. But the core of it, the match-grade balls, the tournament-grade production, has not moved. And the reason it has not moved is the reason that matters. Manufacturing precision at scale is not a skill. It is an ecosystem. Picture a master chef, not the recipe the chef. The years of practice, the calibrated intuition, the ability to taste a sauce and know immediately what is missing. Now picture trying to replicate that chef's restaurant in a city where none of the ingredients are grown locally, none of the kitchen equipment is made nearby, and none of the staff have worked in that style of cuisine before. You could do it, but it would take a long time. And while you were doing it, the original restaurant would not be standing still. That is the dynamic in Yiwu. The yarn winding machine manufacturers are local. The adhesive chemistry suppliers are local. The mold fabricators are local. The quality control calibration expertise is local. The logistics infrastructure, specifically optimized for the full-volume inflated ball constraint, is local. When a factory needs to solve a new production problem, the solution is available within a short drive. When a new specification comes in from a brand partner, the factory can prototype a response using local tooling within days, not months. That cluster effect compounds over decades. And here is the brutal catch for anyone thinking about building a competing supply chain from scratch by the time you have reconstructed even half of the ecosystem. The original ecosystem has had another decade of refinement. You are not catching a stationary target. You are chasing something that is moving. This is what the soccer ball, of all objects, illustrates with perfect clarity. It is not a high-technology product. There are no semiconductors inside it, no rare earth elements, no classified manufacturing processes. It is rubber, yarn, adhesive, and synthetic polymer. Everything in it is commercially available. And yet no one outside of a handful of cities in China can make it at World Cup specification quality, at World Cup volume, at competitive cost. Not because of secrecy, because of decades. Now here is what makes this extraordinary. The soccer ball is one of the simplest manufactured objects that gets produced here. The same logic, the same ecosystem compounding, the same cluster dynamics, the same decades of supplier specialization applies to products that are considerably more complex. And some of those products are not sports equipment. What the ball actually tells you about the world. Here is where the entire story snaps into focus. 3.5 billion people will watch the 2026 World Cup. A significant share of them will watch the ball, specifically the ball in the moments that define the tournament. The free kick that bends around the wall, the penalty that goes under the goalkeeper's arm, the strike from 30 yards that changes the score and the narrative and the mood of an entire country. They will not think about what the ball is made of. They will not think about Yiwu. They will not think about the 10 minutes of yarn winding, or the 90 seconds in the thermal mold, or the sphericity gauge that pulled the units that did not meet tolerance. They will think about the goal. That invisibility, the complete disappearance of the manufacturing reality behind the product, is not an accident of capitalism or an oversight of journalism. It is the designed outcome of a supply chain that has spent decades becoming so efficient, so deeply embedded, so impossible to replicate at competitive cost, that the question of where things come from stopped being a question anyone thought to ask. Now here is the part that no one talks about. The soccer ball is not an exception to how the world's goods are made. It is the clearest possible example of the rule. Yiwu does not just make soccer balls. Yiwu makes Christmas ornaments and zippers and pens and toys and artificial flowers and hardware fittings and promotional merchandise and approximately 70% of everything the global retail system puts in front of you at a price point that makes you buy it without thinking. The city that makes the World Cup ball is the same city that makes the thing you bought at the airport last month and the decoration on your desk and the pen in your pocket. Not metaphorically, literally. The same industrial logic, the same cluster dynamics, the same ecosystem that took decades to build and cannot be rebuilt in less than a generation. What the soccer ball teaches you is not a lesson about football. It is a lesson about what happens when one country decides through decades of industrial policy, infrastructure investment, and systematic cultivation of supplier ecosystems to become the place where things are made. Not one thing, not one category, everything. The ball on the pitch at the 2026 World Cup final is a precision object. Its geometry is mathematically constrained. Its material layers serve specific structural functions. Its production required the simultaneous mastery of rubber chemistry, textile engineering, adhesive science, precision molding, and hand craftsmanship, all of it in the same city, at the same time, at industrial scale. And the country that pulled that off for a soccer ball pulled it off for several hundred other product categories at the same time. That is not a manufacturing story, that is a geopolitical one. And the 2026 World Cup, without meaning to, is going to broadcast it to 3.5 billion people, none of whom will ever think to ask where the ball came from. If this changed how you think about where the things around you actually come from, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Do you think a competing soccer ball supply chain will ever emerge outside of China in your lifetime? Or has the ecosystem gap become permanent?